1, 2, 3, 4, let's get it done. Mic check. Basic classes of functions is titled that way because it's basic. We need to know all these different types, some more than others, but hopefully you guys will remember some of the changes and things that we've done to basic functions. I like to call them the parent functions. By manipulating them, stretching, compressing, shifting, flipping, all that fun stuff. We're going to review that real quick, starting with a bunch of function names. So again, if you don't mind, pause, go to this part of the book and see how much of this you could fill in. If you're worried about having to erase or anything else, just go off and do it on a side sheet of paper, or just think about what you would put there. Do it lightly, whatever you're comfortable with. Go ahead and give that a shot. 1.2, I'll come back, fill it in, go over anything and everything with you. All right, hopefully you came up with at least the function name. The equation form is a little wishy-washy depending on the function. And then the graph shape also can be highly dependent on what we're dealing with. So we'll have some that are pretty straightforward, others that are very generic. Let's take a look. Function name, what's the first function that you should have come up with? That would be a linear function. The equation form, as we reviewed already, has about 3 that we prefer. One in particular, especially for graphing, and that is because we know that this graph shape is that of a line, hence the name a linear function. What follows from that? Next one you should have hopefully come up with was a polynomial function. Now, you may have put a quadratic next, and that is a type of polynomial, and then a cubic, a quartic, and a quintic, and so on. But we're going to generalize this at the start here and just call it a polynomial. What do those look like? Instead of y equals, because it's a function, we can put f of x, meaning it passes that vertical line test. It would look a little something like this. So again, can be very large, x to any power, followed by one less, one less, one less. Remember, we always go in descending order from left to right, listing the highest power. That highest power is actually what we call the degree of the equation. And that tells us how many possible doesn't always have to give us exactly that many, but x-intercepts or zeros. So again, if it didn't have all of this, then we would have our quadratic that we're used to, x squared. Take one of those away though, now it's linear. It just has the x. So anything over x to the first written in this form is going to be what is called a polynomial. So unfortunately, we can't really say what the graph shape is. That is entirely dependent on that leading coefficient and degree, the in other words. So if that's to the 5th power, we know it's going to be an odd value. And those are the types of things that you should have learned in pre-calculus. We call it in behavior. We'll get into more of that, but again, these are just things that we're reviewing. I'm just going to put for the graph shape, it varies by degree. The in, even, odd, those things that we just talked about with symmetry also come into play. So what's after that then? If we're not going to list all the different types of polynomials, we're just going to generalize it. Let me run through the next few pretty quickly here. Power functions, rational functions, algebraic functions, trigonometric, exponential, and lastly, logarithmic. So these are the 8 classes of basic functions that we will list, hopefully remember, and then also manipulate at the end of this section. So I'll give you the equation form for all of these, if I can, the graph, and then we'll move on. So there's everything else. I know it's a lot, but I wanted to just throw that at you real quick, because a lot of these we will see but won't work with that often, at least not in this form. It'll be a different format, more extreme calculus. Algebraic functions uses just that. Algebra, adding, subtracting, multiplying, dividing. So yeah, it's going to vary in both equation form and therefore graph shape. But some of these other ones like the power function, the rational functions, trigonometric, and exponential and logarithmic, you should definitely be familiar with. Again, stuff that we've already seen before, just wanted to do a quick review. So now we're going to define a few of these things. a little bit more in depth. Some of it will be repetitive, like this very first one here that we're going to talk about. We've already spoken about this. What are zeros of a polynomial? When f of x is equal to, yep, you guessed it, 0. And remember the synonyms that these were called? Zeros, what else? X-intercepts, and another one that I'm going to add in, also called the roots of the equation. So next, we're going to talk about polynomials. We went in depth about linear functions and lines and all the different forms of slope and this and that. How about the next most difficult or challenging equation? Well, that would be the polynomial. And in particular, the one that we use the most in C is a quadratic. And if we wanted to find the zeros, would you know how to solve? Do you know how many there would be? And I'm going to tell you right now that there are 3 techniques, and I want you to name them. So if you didn't answer this now, go ahead and pause it, see if you can answer those. If not, we'll discuss it. So do you know how to solve for a quadratic, a special type of polynomial? Well, yeah, we're just going to let f of x, or our y value, our equation, equal 0. So if it's got stuff on the other side over here, we may have to add, subtract, multiply, divide stuff to the other side in order to get it set equal to 0. How many will there be as far as our zeros, x-intercepts, or roots? Well, hopefully you know that it is whatever the degree is. Maybe. Could be less because sometimes we have some that repeat. For example, if we had a parabola that was like this, we would have none because it's not touching. But if we had one here that was facing downwards, then we'd actually have 1 right there rather than the 2 that we normally would have if we just had a parabola going through the x-axis in 2 places. So remember, the degree tells us the number of possible solutions, can never be more, usually will be that number. And then part 3, can you name the 3 techniques we use to solve these quadratic polynomial functions? First was the easiest way, the first way we learned, and that was to factor. Next is probably you're going to say completing the square. No, you're not going to say that. Most people don't like that, but it's something that we have to know how to do. And then the last way was the one that you probably said for number 2, the quadratic formula. Although many of you probably know the quadratic formula by heart, you probably don't know why it's that nasty thing. So I'm going to answer that for you right now by proving it to you, hopefully quickly, because unfortunately, I doubt many of you have seen it unless you've been in a previous one of my classes. I know for sure you have. So I'm going to go ahead and start you with the generic form of a quadratic equation. So here's a generic form of a quadratic equation with unknown values for a, b, and c. Quadratic because it has a degree of 2 in my equation. And as you can see, I'm solving for the roots, zeros, or x-intercepts. So first thing I'm going to do is I'm going to get rid of that c. I just want the x's on this side. So now you can see that I instead no longer have it equal to 0, but I'm going to try to solve this equation for x. So I got rid of that and moved it over because I don't know how to factor this because I don't know what a, b, and c are. So since we're proving this and I can't do this, you guessed it, I told you, you're going to have to know how to complete the square. Problem is, we also like x squared to be the only thing there. So because this is a constant sum number, I can actually divide the whole equation by a. So that would be my second step. Now I got my x squared all alone with that leading coefficient no longer there. Technically, it's a 1. Completing the square is just a way to factor when it's not so nice that you can't factor. I like to skip this step, and what we know has to go in here and here, I want it to be the same so that I can rewrite this as x plus or minus something squared. So what can I put here and here that would add to this? Well, all we ever do is just take half of it and square it, because I know I'm going to have to FOIL distribute this to multiply. So half of that is b over 2a, and when I square b over 2a, I get b squared over 4a squared. But if I'm going to add that to this side, I also have to add that to this side. So that's going to be my next step. I'll take half of this and add whatever that is squared to both sides. Now, can I do that? Yeah, I can add a 5 here and a 5 there if I wanted. You know that that is going to keep this equal. It's just I don't know what the b and the a are, so it looks a little bit funny. Like, whoa, why can you do that? It's the same thing. Well, how did I know to take half? Well, remember, when I multiply this there and I multiply this to that, if I have a half of something here and a half of something here, then I will have this whole thing that I started with. So that's why we took half of this. And that is also why we multiplied times itself or squared it, because we knew that this times this also had to result in that when we factor. So what does go in here? Well, it's going to be my half of b over 2a. So that when I add them after multiplying, I'll get a whole b over ax. So I will put plus the b over 2a. Now, what do I get on the other side now that I've taken this and basically factored it to be this? Well, in order to add or subtract fractions, we need a common denominator. So I'm going to have to end up multiplying this by a 4a over 4a. So I'm going to take the positive thing and I'm going to write that first. And then I'm going to take the negative 4ac. And because I have 4a squared here and 4a squared here, I have that many 4a squareds. Now remember, our whole goal here was to solve for x. The problem is I started with an x squared and an x. And I didn't know what a, b, or c was, so we couldn't factor. We're trying to prove that, so we started completing the square. Because now we have a single x. All this other stuff is going to be stuff we know. A's, b's, and c's represent 1's, 2's, and 3's, okay? Or any positive, negative, whole number of fraction. But now notice I've taken this and gotten it down to this equation, which only has a single x that I can then solve for. What's being done to it? Well, it's being added and squared. So we're always going to start the furthest away and work our way to that x. So how do we undo squaring? Square rooting. Now don't forget, when you take the square root, you got to give me both possible cases. Because what squared gives you 9? Well, that could be 3 or negative 3. So that's why we have to say that we are going to get plus and minus this when we take the square root and undo the squaring. So we're left with x plus b over 2a on this side equals the square root of, now, this big fraction over here is pretty nasty, but I can split this square root to the top and the bottom. That is something that we learned way back when we first learned about roots. We can take a fraction and split it or combine it, but we're going the other direction. So what's going to be left on top is the square root of b squared minus 4ac, but on bottom, I know the square root of that. Because it's multiplied together, I can take the square root of 4a squared and rewrite it as 2a. And I'm almost done. I just got one more step, and that is to get that x by itself. And what is being done to it? It's being added by b over 2a. So to undo that, we will subtract both sides to cancel this out and get what we set out to get. And that was the solutions, the zeros, the roots, the x-intercepts of x. Now notice, we are going to both add and subtract this. And because we have a common denominator, we can go ahead and keep it and do what it says on top, which says to take negative b, both add and subtract the square root of b squared minus 4ac. And that, my friends, is why, unfortunately, the quadratic formula is what it is. Now hold your applause until the end, okay? We're not quite done, but hopefully you got something out of that. Is that going to be what we're doing in calculus? No. But I like to give you something a little bit more than just the basics. Hey, remember this? Okay, let's keep moving on. That's something, unfortunately, like I said, a lot of you guys haven't seen before. And I think it adds value for you to understand why it's that nasty thing, and not just, oh, teachers, math teachers are really trying to screw with us. Look what they created. Well, no, this was the problem. This happened to be the solution. if you can't factor or complete the square, we now have this as a viable option. Pretty cool. Hopefully you enjoyed that, but we got to keep on moving. So why is finding zero so important? What else can we find if we are graphing the function? Think about that for a second. If you haven't answered it already, please do. If you need to pause it and get more time, go for it. Otherwise, why is finding zero so important? Because if it's not a zero, then that means it's either positive or negative, which for us, remember the zeros were when the y, or f of x, equaled 0. Those were our x-intercepts, however many there are. So if it's not 0, that means it's either a positive value, a negative value, positive, or negative. And if you can see how I kind of said that as I wrote it, I know that it's above for my y's, positive, or it's below, negative. We can actually create graphs pretty quickly and easily just by finding those zeros. What else can we find pretty easily? Well, if we're finding the x where y is 0, couldn't we find the y when our x is 0? Of course, and what do we call that? The y-intercept. So all of these things are going to be important if we want to sketch the entire graph. And notice I bolded entire. What do I mean by that? Well, what about everything out here? This is just a tiny little window that we're looking at. Oftentimes, 10 to negative 10, if you have your graphing calculator, is what the parameters will be for both the x and the y-axis. So we want to also be able to find not just where it's above and below, where it crosses through our x and our y-axis. We also want to know what happens way out to the right and the left. We call that the end behavior. That brings us to our next definition. End behaviors are when we want to see what? That's where we want to see what our outputs approach as our inputs approach infinity. So as our x gets larger and larger and larger, what do our y's do? Well, they also get larger, but in the negative direction. Or as it gets negative infinity for our x, what do our y's do? And again, it's all dependent on the function itself. And because that is a lot of words, we want to go ahead and give it a symbol. What do you think approaching means? Well, the way that we've always written it was with an arrow, so we're going to keep it that way. We're just going to use that as our symbol for approaching. And by knowing the degree and whether it's even or odd, along with its coefficient of that degree, it will tell us whether it's decreasing, and notice opposite directions, odd, or if it's even, they'll be in the same directions. And that would be a positive leading coefficient. Okay, all things again that we are just reviewing, you should already know. So let's throw a few more definitions at you. 1, 2, 3, and 1, 2, 4. Think about these, see if you can fill them in. Otherwise, we'll go over them very quickly here. So we just got done talking about the degree and whether it's even or odd and the leading coefficient. That's exactly what these are talking about. If the degree of the equation is, there's two options. Either even, that's what the first two are going to be, or odd. That's what the next two are going to be. If the coefficient is positive or negative, what does that mean that the extremes both approach? Well, if it's even, they're both going to approach the same. But if they're odd, remember they're going to approach opposite. It's going to be for these from left to right. So then the extremes both approach what? If it's even and positive, then hopefully you understood it would be positive infinity in both directions. Same. But if it's even and negative, then still same directions, but now the negative direction, which means negative infinity. Whereas if it's odd, remember it's going to be in opposite directions. So from left to right, how is it going to look? Well, if it's positive, they're still going in opposite directions. That's going to be something like this for positive. It will end positively. To the left, negatively, opposite. So in that case, we're going to say from left to right, positive infinity. But again, if it's odd and going in the negative direction, then we will have a scenario that is going to end downwards. So it will start positive and end negative if it's odd with the negative leading coefficient. So again, can't be for both on these, but it can for these because even think of as the same. Last type of function we're going to talk about is what is called a piecewise function. And I'm going to go over the absolute value with you, which you hopefully remember is this and looks like this. And if we just took 1/2 of this V shape, you can see that this is our line. It's actually our line y equals x, because when I stick in 1, I get a 1 out. When I stick in 2, I get a 2 out, because we know the absolute value means the distance from 0. So if I stick in a -1, then I also get 1. -2, +2. And the way that we say when we stick in these values of -1, -2, and we get a +1 or a +2 out, that's what we call the opposite. And the symbol we have for opposite is negative. For example, if we stuck in -3, we would get out the absolute value of that, +3, the opposite. So the opposite of -3. So this is technically a piecewise function, letting you know that, hey, whether it's greater than or equal or less than, usually we restrict one of them. Doesn't really matter in this case because it'd still be 0. You get this or that. So we want to talk about the transformations that can happen to whether it's a piecewise function or any function. So again, if you haven't tried to fill this out yet, tell me what the effect of the graph would be if you had your function and some constant was just added to it, subtracted. What if it was added or subtracted inside, multiplied by your function, or again, multiplied inside to the x's? Or what about these negative values? Go ahead and pause it, see if you can tell me what effect those things would have on your graph. All right, hopefully you got most, if not all of these. I just wanted to quickly show you what they would all be if you're adding or subtracting at the end of the function, not inside of it. Then since it's not being done to the x, you know that that's going to affect the y. And the y values, remember, go up and down. And y's are y's. We do what they say. So for that, it's just going to be up c units or down c units. But if it's being done to the x value on the inside here, then we know that it's going to be, well, unfortunately, x's are probably x's because they wanted the opposite. So that's exactly what we have to do as well. In other words, we want to try to zero that out. And in order to zero out the x plus c, we would have to do negative, which is the left c. X minus c, that would be positive or right c units. Horizontal versus vertical, x versus y. So same thing here. If you had a c on the outside here, then that means it's not being done inside to the x. It's going to affect vertically the y. And if it's greater than 1, then it's going to stretch it. It's going to go up twice or 3 times as fast. But if it's less than 1, still has to be greater than 0, because we'll talk about negatives in a minute. Some fraction, then it's only going to go up a fraction of what it did before when it was that one function that they gave us originally. If it's on the inside, then it's going to have that opposite effect again for the x's. So if it's bigger than 1, well, now it's going to have a compression. It's going to shrink it down. But if it's a fraction, then it's going to have the opposite effect, and it's going to stretch it. And that negative, remember we said, was the English word opposite. And since it's being done to the f of x, which is our y value, that means it's going to reflect about the x-axis. And all our positive y's will go to negative, negative to positive, opposite. And if it's on the inside, then that means it's going to affect the x in the opposite way. So now all of my positive x's would go to negative, and negative about the y-axis now. So again, all things that we have talked about previously in prior courses that were prerequisites for a reason. Get to practicing this stuff. I got a few examples for you to try to put it all together and see if you can even sketch it all at the end. Good luck. I'll be here if you need any help. Take care. See you guys at the next one.